you a Lipschitz domain. So this is omega. Del omega is Lipschitz. You can write it as a Lipschitz graph with respect to some supporting plane. And if I have u and v harmonic and both non-negative, such that on a portion of the boundary, on this portion of the boundary, v equals to 0. So if I have two non-negative harmonic functions which are 0 on a portion of the boundary, okay, then they have to vanish at the same rate. Which is to say, if I normalize the value at some interiorly scale point, say this point is some e, where u of e equals to v of e equals to 1, then BHP tells you that the ratio u by v is bounded from above by a constant which is universal, depends on the dimension and the Lipschitz character of the domain, and bounded from below by some c inverse, where c is bigger than 0. Okay? So this is the classical boundary Harnack principle. So the first quantitative version of such a principle was found by Dahlberg and Ancona, not together but separately. Okay, so this first appeared, and but you will see that when we prove this estimate in a certain context, some of the primitive version of this estimate had already previously appeared in the work of Hunt and Wheaton. This is around 1970, and this is the paper where they showed that if I give you a Lipschitz domain, then the Martin boundary, which is defined by the Constantinescu-Cornea theorem, so that is a portion in potential theory that I will not go into, but the Martin boundary is the potential theoretic boundary that matches with the Euclidean or the topological boundary for a Lipschitz domain omega. Okay, so but one salient feature of this paper was that one of the key things that was used to prove that the Martin boundary, I will not even try to define what that is at this point, matches with the Euclidean or the topological boundary. It uses a Fatou type theorem, which says that if I give you a Lipschitz domain and if u is non-negative, harmonic, and if I have a Lipschitz domain, then I have a non-tangential cone from inside, then the non-tangential limit, if I go through this cone, okay, to the boundary point, this exists at almost every boundary point with respect to the harmonic measure on this domain, on this boundary. Okay. Subsequently, Dahlberg showed that if I have a Lipschitz domain using the same boundary Harnack, if I have this Lipschitz domain, then the harmonic measure is absolutely continuous with respect to the surface measure. And that crucially uses this boundary Harnack principle that allows you to say that if I take the Green's function, then the normal derivative exists at almost every boundary point. Because if a Lipschitz domain, the normal exists almost everywhere, right? Why? Dirac-Marquez theorem. Okay. So what I'm trying to say through all of this is that boundary Harnack principle has been very important in various problems related to potential theory, and the intimate connection that this boundary Harnack principle is connected to this question that Hunt and Wheaton solved was properly formalized in a very influential work of Jerison and Kenny. Early 80s. Now, this is the importance. This is a wonderful thing, right? If I have two positive harmonic functions, they have to vanish at the same rate. And this doesn't happen for sign-changing solutions. Many polynomial examples show, right? Right? Real part of z to the k and anything, right? I mean, you can just hook up examples where it can vanish at any rate. Now, the thing is that this is one thing, that this estimate is wonderful, but some new interest in this kind of an estimate surfaced in the 80s. So, some further interest in this kind of estimate surfaced in the 80s, maybe around 85 or 86, when Caffarelli showed, and Caffarelli and Athanasopoulos showed that PHP implies, boundary Harnack principle implies that Lipschitz, the boundary in the classical obstacle problem, okay, is C1 alpha. So what happens is that once you have this, that the ratio is bounded, then a very beautiful argument due to Luis Caffarelli shows that the ratio is in fact held. And that is something I will cover in this talk. And when you apply it in the context of classical obstacle problem that I will describe much later, okay? So that will be maybe tomorrow. Then I will tell you that how that principle applies and allows you to show that the Lipschitz free boundary is C1R, okay? So a bit earlier than that, so maybe on this side of the board, in 1980 or 81, because of several importance of boundary Harnack principle, with the exception of this one, there was a renewed interest to establish boundary Harnack inequality in more general settings. So there were two major teams of people who were working on it. One was Caffarelli, Caves, Mortola, Salsa, and the other team was that of Jerison and Kenny. So they generalized this boundary Harnack principle of Dahlberg and Ancona to divergence of AX value kind of operator in Lipschitz domains. And this team of people, okay, were trying to establish the boundary Harnack principle for domains which are more general than Lipschitz. So they established boundary Harnack principle for Laplacian but NTA domains. So what is an NTA domain? So I'll just tell you something. I will draw a picture which is not Lipschitz, and then you sort of connect it in this way. That is, if I stay at a scale invariant point at a distance r, and if another point is at a scale invariant point as well, so this is x, then I can connect it by chain of Harnack balls, overlapping balls. Okay, and the number of such balls will depend only on the NTA character of the domain. And you see that at this point, I cannot write it as a Lipschitz term because such a function will be two-valued. Okay, so but if you have a Lipschitz domain, it is automatically NTA. Why? Because if I give a Lipschitz domain at every point here to here, I have a cone of monotonicity. Cone so that the graph is on the other side, right? That is what characterizes the Lipschitz domain. So then if I have a point here and a point here, then I can keep moving. And at every time, I can double the size of the radius, right? And so therefore, the number of such movements that I have to do would still be something which is more like dimension. So it's depending only on this universal Lipschitz character, okay? Because that will be decided by the aperture of this cone, the angle of this cone, to what extent I can magnify. Clear? So no further discussion. Okay, I have to move fast. So what I will do in this lecture is to cover this beautiful result of Caffarelli, Phase, Mortola, and Salsa. Okay, and what they did in this one was they found out an entirely different contour to prove this boundary Harnack principle, and that gives further light into this whole theory. So what I will do for most of my lecture is to prove this classical boundary Harnack principle in Lipschitz domain. The same proof will apply to this operator, but the proof will be using the idea as in this paper. Okay. Now, before I can even get into this, I need to list some salient features in the proof of the Banerjee-Nash-Moser theorem that Professor Adimurthy talked about. Okay, because it's not just the result, but some of the intermediate steps that I will need in order to prove such a result. Okay. So, Banerjee-Nash-Moser theorem, Banerjee-Nash-Moser. Okay, it says that if you have U which solves divergence of AX that is equal to 0, okay, and then A is, if you form the elliptic lambda inverse and lambda, then U is the alpha, where this alpha only depends on the dimension and the ellipticity character. Okay, you can pretend that A is as smooth as you want. Okay, the important new information is that the C alpha norm does not depend on the smoothness. Okay, so this is in some sense the true elliptic theory. That is, what is the property that is invariant in the class of all elliptic operators? It is this property. Okay, so this is the C alpha theory of Banerjee-Nash-Moser, and as Professor Adimurthy would have told you, I suppose that it applies to Hilbert's 19th problem. But that will be a little bit of a detraction from this event, because we want to stay focused to this. So I will not try to say that how it arises, but you can think that Banerjee-Nash-Moser theorem in particular says that minimizing graph cannot have corners. Okay, a minimizing graph which is Lipschitz has to be C1 alpha. Okay, and then it will be even real analytic. Okay, so that is where so of course I mean that theory of Banerjee-Nash-Moser it was used to cover a larger class of variational integrals, but the first motivation came from the Plateau problem, which is about if I give you boundary values, whether when you solve the area minimizing problem variationally in a convex domain, so the boundary conditions gives you that such a minimizing graph is Lipschitz, but then the question is that whether it's better than Lipschitz, okay? And the Banerjee-Nash-Moser theory tells you that the derivatives have to be C alpha, which solves a uniformly elliptic operator, and then the original function, graph minimizer is C1 alpha. Once you have C1 alpha, then you can bootstrap in this theory and get all the way up to C infinity and even real analytic, okay? So this is where it sort of appears in the Hilbert's 19th problem. Now the other thing is that there is also a Harnack inequality, which is only dependent on ellipticity, which is the Moser-Harnack. I have to use that in my lecture, okay? So that says that if U is non-negative, and let me give it a name, solves 1, and infinities, which is the supremum of U, it solves 1 in T1, it could be any scale invariant thing, okay? So it could be BR, because we can rescale the problem and the ellipticity doesn't change. BR, so let me just purposely write it in BR, then supremum of U, which is the infinity of U, over BR by 2 of the set is controlled by a constant which only depends on the ellipticity times 0 of U, which is the extremum of U, over BR by 2. This is the Moser scale invariant Harnack inequality, but then the thing is that later on it was realized that you can also recover it from the Banerjee's proof. So I will mention some features of Banerjee's proof because they will be very pertinent to my lecture as well. And then when I give the afternoon lecture, I will tell you that how, when I do the Krylov-Safanov, I will tell you that how you can recover the Harnack using that as well, okay? So first, some features of the Banerjee's proof. Now the first thing to note over here is that this immediately implies that U is Helder. From Harnack, Helder follows. So this implies that if U is sign changing, then U is Helder. Why? Because what I do is that, suppose I have U which solves 1 in B1, okay? Then what I can do is that it's a linear PD, right? The one over here. Then I can do is that I can sort of translate the graph, multiply the graph in a way so that I can adjust the oscillation in B1. So I can rescale it and I can adjust the oscillation of U such that the max of U over B1 is 1 and the min over B1 is minus 1. So that means that the graph is over here. Okay, so this is where the graph lies. This is the value plus 1. This is the value minus 1. So when plus 1 means, so this is the 0 level. Okay, so this is the set minus 1, 1. Okay, well, I should put it here. This is the set minus 1, 1. And this is the level 1. This is the level minus 1. Okay, now how do I apply Harnack to get it? What I do is that I don't do much. I just look at the value U of 0. Right? U of 0 has two choices. Either it's positive or negative, right? If it is positive, then it's away from the minimum by a distance at least 1. Agreed? And then this Harnack will tell me that in half the set, it has to be uniformly away. Or, well, said differently, so what I do is that if the distance, so I just do one case and then the other case will follow similarly. Okay? So oscillation is 2. So if U of 0 is away from minus 1 by distance which is at least 1. Okay? Clear? So that means that U is positive, right? U is at least non-negative. So U plus 1, first of all, let's call it B. So B is also a solution to the same equation because I've just added 1. And what I know is that B of 0 is bigger than or equal to 0. Bigger than or equal to 1. Okay? So if I apply the Harnack to B, that tells me that the infimum of the supremum of B, okay, the supremum of B over B half is less than or equal to, okay, the supremum, well, I need the infimum actually, so that the distance is kind of the same. So the infimum of B, okay, over B half is less than or equal to 3 times B of 0. Agreed? Agreed? So what does it mean? This means that in half the set, you cannot get too close to minus 1. So therefore, I am able to sort of truncate a little part where this constant, you can find it more explicitly, So the amount that you truncate is like 1 minus 1 by C. Agreed? If you write it out, this is what you get. Is it clear to everybody? Because this is CV of 0, this is at least 1. So I can remove this. Okay? Clear? So, and on the other hand, if the other alternative is there, that U is away from this by distance at least 1, then in half the set I can truncate over here. So either I can truncate over here by some theta, or I can truncate over here in the other case by that theta. But in both cases, the oscillation has fallen to 2 minus theta in half the set. So therefore, in both cases, what you get is that the oscillation of U over the half is equal to 2 minus theta. And that is 2 minus theta by 2 times the oscillation of U over V1. And this is your oscillation V2. So that means that the oscillation of U, so let's call it some other name, gamma. Okay. So oscillation of U is less than equal to gamma, where gamma is strictly less than 1. Depends only on ellipticity, because this theta depends on this C in the Harnack, and therefore only on ellipticity. So therefore, what you have is that you have this recurrence relation. Okay. If you iterate this inequality, you just get that oscillation of U R is less than equal to constant CR, where alpha depends on this. Is it clear? Because at every level, so oscillation here is 1, so and then 1, and then in the next level, it has fallen to half, 1 by 4, it has fallen further, so you can sort of join it by hand. Do you want to see a more analytic proof? I mean, what is this alpha in terms of this gamma? No. Okay. So this is one thing. The other thing to note is that one of the how the de Giorgi's. So this is like once you have Harnack, how do you get Helder? But what is the key feature of de Giorgi's proof? One is, so what are the steps in de Giorgi's proof? De Giorgi, L2 to L infinity. Right? What is L2 to L infinity? When it what it says is that if you know that in measure it's small, okay, then in half the set it is uniformly small. Say that so L2 to L infinity for a non-negative subsolution. Okay. So let me put it in a certain way. So that what it tells you is that if I know that minus 1, 1, if I know that if I am a non-negative subsolution, okay, so this is the set and this is the level 0, and if it is like this, okay, that means that the L2 norm is very small, okay, then in half the set, the L infinity norm has to solve. So this means that this is a fake picture and it has to cut somewhere over here. So this is a fake picture. And something in, so this is in minus half or half. And what is this telling you? It is telling you that the concavity character is kind of controlled, right? And for a subsolution, at least heuristically, you expect that the convexity character should dominate, right? Think of the Laplacian, okay? So this is the first step of the proof. And the second step of the proof is L infinity to C alpha. Okay? And there comes the important measure uniform lemma, which uses the pointer inequality that you would have mentioned. So measure uniform lemma. Is it visible, this part of the board, or maybe I can use the other part? So the measure uniform lemma. So measure uniform lemma. That tells you that if I have U, or let me call it V, non-negative solution, such that V is less than equal to 1. I can do that. Why? Because of the first step, I know that it is L infinity bounded. Okay. So this is my say 1. Okay. This is the maximum. And if I know a set where V equals to 0 is bigger than equal to 0, that is, I know something like this. So this is how the graph is. So let's pretend that it can even go. So let's remove this. Okay. So that V is less than 1, because I just want to draw a graph which is like below this level. So suppose that in minus 1 to 1. Okay. And so I look at the set where V is less than equal to 0. But then I can always truncate it at 0. Why? Because V plus is also a subsolution. Okay. But so let's look at this set. So this is the 0 set. So let's call this set E. So what I know is that this set E, measure of E, is bigger than equal to 0. That is, on a good chunk of the set, V is away from the maximum 1. Okay. By a distance which is 1. Then what the measure uniform lemma tells you is that in half the set, which is minus half to half, well, I don't know where to go the half, so let me just exaggerate this picture, okay? Minus half to half, it cannot get too close to the maximum. Of course, when you have the comparison principle of the strong comparison principle for harmonic or subharmonic functions, you know that there cannot be an interior maximum, right? What this lemma is telling you is that this is a quantitative one. Where this quantitative, how much it has to separate from the maximum depends only on the ellipticity character. So therefore, in half the set, it cannot be too close. That is, it has to sort of curve somewhere over here. So there is a separation. So if this distance is bigger than theta, then there exists a delta depending only on theta and ellipticity, such that V is less than equal to 1 minus delta in V half. Okay. Now this is enough to prove. So this is enough to prove the, again, by the same argument as for Harnack, this is enough to prove Helder continuity. Why? Because again, I don't normalize the oscillation to be where do I have the picture? The picture, well, the picture is quite sort of distorted by now. So this is the level +1, this is the level 0, -1, 1, and this is the level -1. So again, I have a situation where oscillation of U over V1 is 2. The maximum is 1 and the minimum is -1. Then what I do is that in that entire set, this is like V1, but a 1D picture, at least U plus or U minus is equal to 0 half the time. Half the set. That is, in a good chunk of the set, at least U is away from 1 or U is away from -1. Because U plus and U minus cannot be both positive at the same time, right? So therefore, at least in half the set, U plus is 0 or half the set, U minus is 0. Okay? So let's just look at one possibility and then we look at the other one. So let's move this up in a more organized way. So I keep this and I remove the history. If it happens that U plus, so suppose U plus is 0, half the set. So therefore, if I apply this measured uniform lemma over there, the measured uniform lemma, NU lemma of T dot G will imply what? This will imply that U plus is less than equal to 1 minus some delta in V half.
Almost everywhere or literally everywhere?
Doesn't matter because I will assume everything is smooth. Okay. The important thing is that the estimate should only depend on the ellipticity because then I can modify, solve a one-dimensional problem, and then get estimates for the original problem. So that is not the central thing, but yes, almost everywhere is also fine. Okay. So once this happens, so then it means what? In half the set, at least U plus has come down, right? That means there's an oscillation U in V half and again fallen less than 2 minus delta. Why? Because the top has fallen. The top has fallen by delta. Even if I assume that the bottom edge still is -1, when then the gap has reduced, right? So again, you get this voltage that you need. Okay. So this is one thing. And if you look at this, stare at this estimate, the oscillation lemma properly. So what does the Dijorji's oscillation lemma tell you? Oscillation lemma tells you that I'm just distorting the symbols. Okay. So that tells you that oscillation of U, I don't care where it's defined, V half is less than equal to some 1 minus theta times oscillation of U over V1. Okay. Now, if you iterate this inequality backwards, what you get is that a bounded, so this implies in particular the Newman theorem that if you have U bounded, divergence of A prime U equals to 0 in Rn, and U is constant. Right? Because if it is not constant, then at least at some scale, which I can happily rescale it to 1, okay? At least at some scale, the oscillation has to be of U in say V1 after rescaling and by multiplication by constant is bigger than equal to 1. And then what does this tell you is that then in twice the set in V2, it has to be bigger than 1 by 1 minus theta. And then in V2 to the power k, maybe 1 by 1 minus theta to the k or k minus 1, doesn't matter, you figure out. And therefore, you cannot possibly stay bounded, right? So therefore, at no point you can have any sort of distortion of the function because that will sort of reflect in the values, which will sort of magnify later on. So this is kind of the doubling property. Okay. So this is another proof of the Lewis theorem. So now let me sort of go back to my boundary Harnack. So I have already taken 20 minutes or 25. So I'm running really late. So now let me go back. So now the first thing that I will need is the following, that if I take u to be non-negative, okay, Laplacian equals to 0, u is bigger than or equal to 0, and on this part of the boundary u is 0.
I'm sorry, is it possible to give that proof that you have?
I have to decide whether to give this proof of Caffarelli modulus also or Banerjee's.
Maybe a simplified version of it.
I cannot. Okay. Because the time is very less. So I wish I could. In fact, the thing is that when I talk about the classical obstacle problem, I will revisit some more ideas in the proof of Banerjee. But because the symposium is around Luis Caffarelli, so let us keep that feature of this. No, it's a very good point because I think without that proof, the feeling is very hard to have. Okay. But I can just tell you in words that every time you pick up some zero set, you start with u plus, which picks a zero set, then what happens is that then because of the pointer inequality, there is a good chunk of the set that if I truncate it at the next level, then you enlarge the zero set a bit. Okay, so you keep truncating it till you reach a point that you run out of the measure of the ball of radius 1. Okay, and therefore the thing is that at that point you will get that the oscillation is predicted. Because what does the Banerjee thing say? The first L to L infinity lemma. It tells you that if u in L2 is small, that is, if u, the set, is very large, then u is less than or equal to half, if we have, right? So you have to see that how much of zero set you need to pick to reach below half in this, right? If you start, so this u is actually u plus, okay? What you do is that you truncate this u plus at higher and higher dyadic scales, and because of the pointer inequality, you pick up a good chunk of the zero set. Yes?
I mean, just like the point.
No. So at this point, I have to be more dictatorial, and I just need to proceed further. Okay. So now the thing is that let's go to this. Okay. So now if I extend u by 0 from this set, then u is subharmonic. While you have a line which is harmonic, okay, it becomes 0 if an extended convex function subharmonic. Okay. Well, this is not a proof, but what I'm trying to say is that you sort of use a Bilipschitz transformation, move here, you get a divergence of A gradient equals to 0. Okay. Then with 0 boundary condition, you oddly reflect it. Okay. On this set, the coefficients also get appropriately reflected. Okay. Some of the coefficients are evenly reflected, some in the odd way, which are these AIN entries. Okay. I will not write down the details at this point because they will anyway come later. And then once you have a solution in this entire region, this is just the Schwarz reflection principle by reflecting the coefficients appropriately so that ellipticity is not lost. Then if I take the u plus corresponding to that, that would precisely be this function, right? If I come back. Clear to everybody? Because when I deflect it, the new u tilde is negative here. So if I take u tilde plus, it would simply be, if I come back to my original coordinates, this will be u here and 0 everywhere else. Okay? So now good. So now the thing is that, how does that lead to, if I know this, okay, and if I know the measure oscillation, measure uniform lemma, then I can tell you that if I have a non-negative harmonic function, which is 0 on a portion of a Lipschitz boundary, then it becomes 0 at a Helder rate. Why? Because of the following. So what does this tell you? So you have this B1, U is subharmonic, so let this boundary point be 0, U is subharmonic, and because it's a Lipschitz domain, so this is a very nice picture, right? But the domain could be worse than this. So this could be a good side of the domain, and this is the bad side, okay? But no matter what happens, a Lipschitz boundary is one where outside you have a cone and inside you have a cone, okay? So therefore, there is a good chunk of the set, okay, which is living outside, okay, over here, which is the one over here. Look at this picture. So U is harmonic, okay, and U is bigger than or equal to 0, and on this part U is 0. So at least there is a cone outside that goes out. So therefore, if I take a ball of radius 1, there is a good chunk of the set where U is 0. Okay, so U0 is bigger than or equal to some theta times B1, where this theta depends on the angle of this cone, the Lipschitz character of the domain. Then what does the Banerjee's oscillation lemma, major oscillation lemma tell you, or uniform lemma? Then this means that oscillation of U over D half, because finally if you have a non-negative subsolution and if you have this measured information, that automatically gives you Helder. So you don't need a solution. Okay. At the first step you need, because you need to know whether it's U plus or U minus. But after you have this information in this specific case, the same lemma applies to a subsolution. Yeah. So therefore, the thing is that this particular implies that the oscillation of U is less than equal to some 1 minus delta times the oscillation of U over P1. Now, one thing I'm a bit forgetting, because when I was interrupted, did I show you that how this measured uniform lemma gives you a Helder continuity? Did I? From this one, did I show? Harsh, do you remember? No. But I want to say that how this measured uniform lemma gives you the Helder continuity. Did I show this? Probably not. I think I did. I think I did. This is what I did. Okay. So because I was not sure when I was interrupted. Okay. So this is what it is. So this happens, right? So this means that if I have a non-negative harmonic function, so that means that in half the set I have picked up well. So this, if I iterate, what I get is that oscillation of U over any B1 by 2 to the K is less than equal to 1 by U delta to the K. And this is like a C alpha continuity, right? Clear? So this gives a very slick proof of the fact that if I have a non-negative harmonic function 0 on a Lipschitz boundary using the Lipschitz character of the domain, where am I using the Lipschitz character? That there is a cone outside where the measure is good. Okay? Then I can apply the Banerjee's lemma, the interior version of the Banerjee's lemma, to get Helder continuity. So this is one feature that I will repeatedly use. So any non-negative harmonic function 0 on a portion of a Lipschitz boundary is Helder.
Also have the boundary estimate.
Yeah, so it just comes from this, right? So this is one feature. And now the next thing that I have to say is, so now I am going to the proof of Caffarelli phase modulus alpha. So given a Lipschitz boundary, what I do is that I flatten it. So given a Lipschitz boundary here, I use a bi-Lipschitz transformation, and then I am able to deal with a flat boundary. I need to see how the coefficient changes, right? So what I'm doing is that I'm defining U tilde to be U of psi. So for the weak formulation of U, what I have is that grad of U tilde, I have to evaluate of phi, grad of, and suppose I'm using the test function. So let me call the test function phi of, well, this is a bad notation. So let me call the test function B, okay, of psi. And then there is a volume factor. If I use graph coordinates, the volume factor is more or less 1. Okay, so I don't care. But anyhow, if you want to put it in the most general scenario, you do, and this will be 0, right? But the change of radius. I need to just know what the coefficients are in the new coordinates. Okay, and whichever way I go. So how does that change? I want to show that once you map it here or the other way around, I have to say which way. So well, maybe the other way. So this way is fine. Okay, because only then this is. So U tilde of phi. Okay. So I want to know how this changes. Okay. So this will be 0. But if I have to evaluate this part, what does it become? The grad q phi part becomes the Jacobian of phi transpose. And this is again Jacobian of phi transpose grad p. This is the volume factor. So volume factor, I will finally put it here. So assume that the volume factor is 1. Because the volume factor is some positive constant, this is not going to affect the ellipticity much. Okay, and now I move this here. So call this matrix A, and this is A transpose. This is also A. So then, if I move it here, this becomes simply A transpose A grad U tilde grad B equals to 0. And this is the positive matrix, right? A tilde A is a positive matrix. So this is, therefore, all I'm trying to say is that if I use the bi-Lipschitz transformation, I pick up a boundary, okay, where I get that inside it is divergence of A grad U equals to 0. Where A is uniformly elliptic. And the ellipticity character depends on the bi-Lipschitz transformation. Clear? Because once you have this, you have a volume form, but the volume form you move inside, okay? And then you have a divergence from representation of the PD. Because what is then the PD? The PD satisfied by U will be, U tilde will be divergence of AT, A, U tilde, which is volume factor inside, equals to 0. And this is your new A. Clear? This is your new A. Anyway, so you see that when you use a divergence from PD, you only pick up one derivative of the transformation. And this is different from the non-divergence form scenario, where things are much harder, right? Because when you open up the structure, you are bound to pick up two derivatives. So that requires very different arguments. Okay? So this is one of the key insights that they had. Of course, I mean, this is something which was well known. But once you are in the structure, then you are able to sort of revisit some of the salient elements in the proof of DiGiorgi's proof. Okay, so this is what I will do now. So now what I have is that I have two non-negative solutions in this upper half space in this field. Okay, I have U and B. So let me call the operator L to be divergence of A grad. I have LU equals to LP. Property. So U and B are non-negative. And you were staring at me for long. So I thought that you were upset. No, I'm just joking. It's not. What you? Okay. I have to pick on somebody. Otherwise, it becomes very boring. This is there. Okay. Fine. And then after that, now what I want to show is the first estimate will be the Carlson estimate. I mean, I don't know why it is called Carlson estimate, but at some point, Caffarelli started calling it the Carlson estimate. So in fact, I must also say that when I explain this Hunter-Meaden, there is a further precursor of that paper, which is a paper due to Carlson in 1962. So again, when you look at all these papers, you see that many of the elements that led to the final proof of the boundary Harnack, they were already present in these papers, all these harmonic measure estimates and so on. But the key new feature of the Caffarelli phase Mortola salsa theory was an entirely different geometric perspective. And that is why I thought that this is a very appropriate topic to be described in this symposium. Okay, so now we will get to that, and you will see that it's a very beautiful argument. Okay, in their paper. So the first one is, well, I don't know why I did it. Carlson estimate. Carlson estimate. So what I have is that I have U non-negative, and what I do is that U equals to 1, LU equals to 0, and U non-negative, and U is 0 on this part of the boundary. Okay, U of E at some point is 1. Then I want to say the Carlson estimate tells you that supremum of U in this set, supremum of U over this set, which is say half the set. So this is say Q1, this is say Q half, is less than equal to some M. But this M only depends on, it's a universal thing which only depends on the ellipticity character, which further depends on the Lipschitz character of the original domain from where we came, and so on. Okay. This is something to notice, right? Because U is 1. The fact that this is uniformly bounded requires a proof. Why? Because this is just telling you that if I have a one-sided restriction that is U is non-negative, it cannot develop a big cliff or a spike. Okay. In this set, it is controlled. And this uses a compactness argument, which is one of the very, one of the tools that Luis Caffarelli has used in many of his works. Not just the only tool, but one such tool. And I really like this argument. Okay. So now suppose I want to, what do I want to do? I want to get hold on this M. I do not want this M to be too large. Okay. So suppose U of E is M. So, suppose U over D half is equal to M. This is a picture. This is a point where U equals to 1. Okay. Now I want to tell you that if it is M, then the point, so there exists a point, say x0, such that U of x0 equals to M. Now this point cannot be too close to the inside. because if it is too close to this point, so if this is too close to this point, then by Harnack, all the values are the same. All the values in this chunk is comparable to 1. So if at all it is a large M, it has to happen close to the boundary, right? And that is what I need to quantify. So suppose the point x0 is here. And this is the distance to the boundary. So let D be distance of x0 from the xn axis. So this is the xn direction. Or, well, not the xn direction, so this is xn equals to 0. Okay. Okay, so I need to quantify this. Okay, how do I quantify this information? Well, if this is V, okay, if whatever this is, okay, clear? So the number of movements that I need to make. Okay, so number of movements. So this D is like 1 by 2 to the k, right? It is like some dyadic scale. Okay, so this distance is like 1 by 2 to the k, and this is the k that I need to quantify for you, right? How close it is to the boundary. Well, if this is the point, if this is M, okay, then the number of balls that this time I will take 2 to the k minus 1, then I will take 2 to the k minus 2. So in at least a k number of steps, I will be able to reach this point, u of t equals to 1, right? Agreed? So what does it mean? So if I apply the Harnack in these successive chains, what I get is that this u of x0, is bigger than is less than equal to c to the k u of e, it is 1. Right? Clear? Now, what is this u of x0? This u of x0 is m, has to be less than equal to c to the k. Is it clear that every time you apply the Harnack on these chains, the number of such balls that you need to take, because you multiply every time by a factor 2, the number of such balls is comparable to k. And I want to get a hold on this thing. So here is the thing. So M is so this is there. So therefore, this k. So k times. So if I apply the log, so k will be bigger than equal to, right? Here, k will be equal to this. So therefore, then this 1 by 2 to the k. So minus k. So I just want to write down this exact number. So minus k is less than equal to minus m. So 2 to the minus k will be less than equal to 2 to the minus ln cm. And if I sort of just apply some basic algebra that we learn in high school, this is simply m ln c2. So this is your epsilon, and this is the ellipticity. So therefore, if there is a point at the boundary, okay, if I try to match the value over here at m, then this distance has to be m to the at least m to the minus epsilon, or smaller than that. Okay, here. So there is a point x0 which is at a distance m to the at most m to the minus epsilon to the boundary, where this value has to be m. So this is what Harnack does. If it sort of sees the positivity somewhere, okay, it is otherwise non-negative, it sees the positivity somewhere, it ensures that this positivity is perceived all the way up to this point where the value has been normalized to be 1. Okay. Good. So now, so this is the point x0, which is at a distance m to the minus epsilon to the boundary. Okay. Then what does the de Giorgi's theory tell? De Giorgi's theory tells you that the oscillation, because the oscillation has to multiply in twice the set. So therefore, in 2m's or maybe 400 million times m to the minus epsilon. So let me just call it like some k times m to the minus epsilon distance from x0. Okay, so this is the cube, right? So if I do this cube, so if I multiply this cube enough by a constant factor, and here it is m, this point it is m, at some point in this multiplied factor, which is like, so this distance is like Km to the minus epsilon, my E is very far from here, which is crossing the board, okay, that I cannot see. Then at some point over here, I have to have that there is some point in this set where this value is 2m, right? Because if I sort of apply this doubling inequality, the backward oscillation lemma, more and more times, at some point I'm going to cross twice the value over here. So there is this sum x1 such that x1 minus x0, okay, is less than km to the minus epsilon, such that u of x1 is bigger than equal to 2n. And now this x1, so let me draw another picture to convince you more. So this x1 is now at a point over here. But at x1, the value is this much, right? So therefore, if I just apply this argument again, then I get that distance of x1 from the boundary is what? Is less than km, 2m, the minus epsilon. So this is now the point x1, which has shifted further close to the boundary, right? Because the value has doubled. Then again at this point, so this is at a cube, which is like 2m to the minus epsilon, right? The size of the cube. Now, at least again, by the same magnification factor over here, I can find the point x1, so x2, where the value has further doubled. And this k doesn't change, no matter whether I have m to the minus epsilon or 2 to the m to the minus epsilon. Why? Because it's a constant factor of that, right? Because that doubling inequality, which is the backward de Giorgi's oscillation lemma, is a uniform feature which only depends on ellipticity. So there exists some x2 such that x2 minus x1 is less than equal to x2 minus x1 is less than equal to k times 2m minus epsilon, such that u of x2 is bigger than equal to 2 square m. And now I continue. So every time, again, I can take a cube, then I find another point which is even closer to the boundary, where the value has further doubled. So I find points xk such that xk minus 1 is less than equal to k times 2 to the k m minus epsilon. See, I don't want to be very pedantic about 2 to the k or 2 to the k minus 1 because it only changes my little, okay? Such that u of xk is bigger than equal to 2 to the km, right? I can keep continuing. Now, so what is the distance from x0? So x0 is a point in my cube over here. So xk minus x0, if I calculate, this is less than equal to a geometric series, which is what? So this is less than equal to k times summation of 2 to the k m minus epsilon. So here is the picture. Let's remove this point. U is 0, U non-negative, U is 1, and I want to control U in this set. If this value is very large, so I find the sequence of points xk's, and if this m is very large, then I don't slide too much to the left or the right, so I never cross Q1. So if I take this m to be very large, which is in my control, then I can control this value to be less than 1 by 4 or 1 by 10 million. I don't care. But as long as I'm away from this boundary, I am fine. So I find a sequence of points which gets closer and closer to the boundary, right? Because at every time the distance is sort of decreasing. So xk goes to some x infinity, which is not on the right or the left, but it is somewhere over here, okay? Where u of x infinity has to be infinity. But this cannot be because on the boundary, u is 0. So in the very first place, if in half the set, which is over here, if the value crosses too much beyond a certain threshold, I can find a sequence of points which doesn't slide too much to the right or left and goes to the boundary where u becomes infinity, and that cannot be. Okay, so this is the Carleton estimate. And it's a beautiful application of compactness argument. You will see some other feature of this argument also in a later proof of Krylov and Safan. Okay, so you will see lots of hopefully good ideas. I don't know how the exposition is, but the mathematics is used. So this is the Carleton estimate. Now the other thing that I need to cover, well, I'm still running short of time, is that in order to prove the boundary Harnack, okay, the other ingredient that I need is the equivalence of the Gibbs function for the Laplacian and this. So the next result that I want to prove is due to Lippmann, Stampaki, and Weinberger, that says that if I have divergence of A value, which is LU equals to 0, then the Green's function of L which goes anywhere is comparable to mod x minus x naught to the 2 minus L. And in dimension 2, it is comparable to minus log. Okay? So therefore, it tells you that if I have a uniformly elliptic PD, uniformly elliptic operator, the Green's function is comparable to the Green's function, the fundamental solution of the Laplacian. And this again is a consequence of the equivalence of the L capacity and the 2 capacity. So what is capacity? So how do I prove this? So this was proved in an earlier paper, Littmann, Stampakia, and Weinberger, and this was kind of the key punchline that allowed them to show that if a point on the boundary is regular for the Laplacian, then so it is for any uniformly elliptic operator in divergence form. Non-divergence is an altogether different ballgame. Okay, I won't even try to mention that. So that was a very big insight. So how does so for that you need to know one ingredients in the proof are the following. L capacity is comparable to the 2 capacity. What is the capacity? Let me sort of give you a very rough description of it. So I have a compact set and I have a big domain omega. Okay? And I place a conductor over here. The capacity is the amount of charge that you need to put on this conductor in order to make the differentiable capacitary potential to be 1 at K. So this is my K. And capacity is the total charge that I need to put. So in equilibrium, the charge will distribute. So in the omega minus K, this will be harmonic. Okay. And what is the total charge? The total charge will be the flux that goes inside. Okay. The charge will distribute. So the total charge, which is the capacity of K in omega, will be u mu in K, boundary of K. Right. So this is my K. Okay. The total charge will distribute because it's a conductor, but because it is harmonic inside, harmonic in this annular region, so to speak. Okay, by divergence theorem, because it's harmonic inside, u mu in is minus u mu out. Okay, on this. So the 2 capacity of K in omega is equal to minus u mu over 10 omega. And now u is 1 over here, right? So this u is 1 over here, 0 over here. Okay, so I can multiply with u. If I multiply with u and use divergence theorem, this is simply u square by 2 mu. Okay. And again, if I use the divergence theorem, this would simply be this will simply be the fraction of u square by 2 over omega minus K plus minus, doesn't matter because soon it will be 0, u square by 2 mu over 10 omega. But now this is 0. Why? Because this is u mu, and u is 0 on this boundary. So this term disappears. Okay. And now if you elaborate, sort of open it up, one term is u Laplacian of u by 2, and the other term is 2 by 2 u Laplacian u by 2 or by 2 is not there. So the u whatever doesn't matter, but Laplacian u is 0. The other term is 2 grad u square by 2. Right? So 2 cancels. So this 2 capacity of K on one hand has this characterization, which is the flux outside, but it also has the inward characterization, which is the grad of u square over omega minus K, where this u is the capacitary potential. Okay? And now you see that the L capacity is similar. Why? Because A grad u is comparable to grad u square. If you use this for all functions, you simply get, without any further details, because this is a very soft point, that L capacity is comparable to Laplacian capacity. Okay? Is it clear? Because you can sort of compare the minimizers by this energy. Because the quadratic form is comparable. Good. So once this happens, so now I will tell you that this is enough to show that the Green's function is comparable to this. And I would have wanted to give a detailed proof, but the way I'm running, I have to give heuristics, but that is the central idea, okay? The rest are pushes, and this will be taken from me. So now what I have is a domain, okay? And I want to understand the behavior at a pole. What I do is that I take a certain region at some scale invariant distance r, which I can normalize to 1. Doesn't matter, right? Clear? So then suppose that this is the Green's function. So let this be GL and other is G. Okay. Suppose this is the GL. Okay. So let the maximum value over GL, the value of GL is say M1. This is say M1. And suppose so 0 here, and suppose the maximum value of the other one, which is the Laplace capacity, or the other way around, is M2. That is on this annular. Now by Harnack inequality, so this value is M1 for the GL, and this value is M2. Now if I know how to compare M1 and M2, then I am more or less done, because by Harnack, all the values in this annular are comparable to one another. There is a scale invariant Harnack inequality. Okay? So I just need to say that M1 cannot be too large compared to M2 and vice versa. Because what happens is that if I have this Green's function, if I scale it to the level of the capacity, so what is the property of this Green's function? The property of the Green's function is that minus A grad GL dot mu to be 1 and minus del G, let's call it G2 of del mu equals to 1, right? Because if you solve the Dirichlet problem with one boundary value, the solution is 1. Okay, this is a reflection of that. So now, so this is always true. Now, if I scale it to the level of the capacity, so if I take U1 to be this value divided by M1, so I'm scaling it to the level of the capacity, GL by M1. Okay, so GL by M1 is what? I scaled it down to 1. So now in the new picture, in the same annulus over here, this is the X dot, and I have here, then this U tilde, U1 is more or less, U1 is like 1, right? And this is harmonic here. So this is the capacitary potential of this BR in omega, right? So let's call this set B without even knowing whether it's BR or B1. Okay, so the L capacity, of B in omega, which is the outer boundary, is simply the Neumann derivative of this is equal to minus A grad GL mu over M1, right? Because I said that these capacities have this characterization, this is the outward flux. But then I know that this value is 1. So this value is like 1 by M1, right? Because the top is 1, if I divide by M1, this value is 1 by M1. Likewise, if I take U2 to be G2 by M2, then the 2 capacity of B in omega is simply minus del G by del mu divided by 1 by M2, and this is equal to 1 by M2. Okay? So this is again the 2 capacity in omega, and this is the L capacity in omega. So when you have to argue formally, you have to say that one is contained in the other and vice versa. You have to take the max of one and the min of one, but they are all comparable to one another. So you will still get a similar thing, except that this set will be replaced by something that contains this B, and this set will be replaced by a set that is contained in B. And then you can compare the same way, okay? It's a very standard thing in our business, okay? But once you have this formally, what you see is that because L capacity and 2 capacity are comparable to one another, and the L capacity is 1 by M1, and the 2 capacity is 1 by M2. So 1 by M1 and 1 by M2 are comparable to one another, which is to say M1 and M2 are the same, which is to say that this cannot be too high compared to this. So the Green's function, and this happens at every scale invariant distance, so that tells you that the Green's function is comparable to that of the fundamental solution for the Laplacian. Okay, good. So this is done then. Now I get to the proof. Sure. So now, what is my scenario that I have? I have this domain, okay? I want to show that the ratio is found. So what I do is that I assume that UE and V is equal to 1, okay? Somewhere over here. Then by Harnack, all the values in here are like 1. And what do I need to control? I need to control the ratio in B half. If I have that UE equals to BE equals to 1, then I want to say that in Q half, Q by B is bounded from above and below. Right? This is what I have to say. by universal constants, okay, depending on ellipticity, this, that, whatever, okay. So let me draw this picture again, because many times I will need this picture. So what happens? So here is the thing, here is 1. So Harnack tells me that everywhere it is 1. So this is the bigger cube, everywhere it is 1, okay. Here the values are between 1 and 0 for 1, and here the values are between 1 and 0. And U and V are trapped in between, right? So what I do is that I try to compare the best case scenario with the worst case scenario. So the best case scenario, or depending on what is best and what is worst, the one extreme scenario is that U is 1 here, 1 here, and 1 here, and 0 here. And so this is U equals to 1 here, U equals to 1 here, U equals to 1 here. But here both U equals to V equals to 0. And for the V, which is the worst case scenario, will be that V equals to 1 here, V equals to 0 here, V equals to 0 here. And then I want to show that in half the set, U is controlled by a constant times V. Of course, V is controlled by U by comparison principle, but U controlled by constant times V is just telling you the doubling property of the harmonic measure. Because the value here of V is the harmonic measure of this part of the boundary. Suppose I think of this as the boundary, and the value of U at this point is the harmonic measure at this point of this part of the boundary. So this is just telling you that the harmonic measure of this part is up to a constant dominating the harmonic measure of this entire thing. So this is the doubling property of the harmonic measure. And again, what I am writing all is wrong, because this is like a two-dimensional thing, but trust me, this proof is not two-dimensional. There will be several faces, so there will be like similarly 1, 0, 1, 0, okay? So you look at all vertical faces, put it to be 1, okay? This is just for demonstration. Yeah? I mean, I cannot do much, because the thing is that I have to recall for you a little bit of the picture here. So now how do I do it? Now first let's look at 1. So what I do is that the value of U and the value of V in this set can be controlled by the Green's function, okay, with pole here in some set over here. So what I will say is that both U and V are controlled up and down by the Green's function. So at a pole at some, let's call it x0. Green's function at a pole at x0 and at some bell. So both U of x0, U of y, and V of y are controlled by Green's function over here. Okay, and this is the same as, because of symmetry, this is the same as x0 y. So I will be using the symmetry at some point. Okay, so now let's first control V. So V is 1 here, V is 0 here, V is 0 here. So let us write down the situation for V. So V is 1 here, 0 here, 0 here, 0 here. So what I do now is that I take 1 minus V. I take some V tilde, which is 1 minus V. Then what is V tilde? V tilde will be equal to 0 here. V tilde will be equal to 1 here. 1 here. V tilde will be equal to 1 here. And V tilde will be equal to 1 here. Right? So this is 1, 1, 1, 0. Now, since this is 0, okay, 1 minus V, this is non-negative, okay? Well, I've drawn two better pictures. So let me sort of scale down this picture a bit. So this is my V tilde, okay? So V tilde is equal to 1 here, 0 here, 0 here. Sorry, V tilde equals to 0 here because it's 1 minus V, 0 here, 1 here, 1 here, and 1 here. Now again, I can stretch it by 0, right? I can extend it by 0. It's a non-negative subsolution, right? And there is a good chunk where it's 0. Then what does the de Giorgi's oscillation lemma tell you? That in half the set, which is over here, V tilde should be smaller than 1. So if V tilde is smaller than 1 in this set by some ratio, which is like maybe 1 minus some lambda, 1 minus some theta, okay? And if I go back to V over here, that means that V has to be sufficiently large over this set. That means that in half the set over here, V has to be sufficiently large. Because if V tilde has fallen and V tilde equals to 1 minus V, then it means that V has to be bigger than equal to theta, right? So I go here. So V is bigger than equal to theta, then I have 1 here, then by Harnack I can propagate the positivity. So that means that on this ball over here, okay, on this ball over here, so what is y? So y is the point here, okay, okay. So then b is bigger than equal to some another constant theta 1 over here, right? Why? Because here b is bigger than equal to theta, and then by Harnack I can propagate the positivity, and I'm far away from the boundary, okay. So b is bigger than equal to theta over here. I can move inside, right? Because these are all at distance from the boundary. Clear? Because this is at a distance from the boundary, this is at a distance from the boundary, this is at a distance from the boundary. So good. And what do I know of the Green's function? Green's function is like the Laplacian, right? The Green's function in this scale invariant region, which is like size 1, the Green's function L is less than equal to some k, right? So therefore, what it tells you that k by theta times b is going to dominate over GL on the boundary, right? On this boundary, k by theta, let me call it some k tilde times b dominates g on this part. But on this part, the Green's function is 0 and k times b tilde is bigger than equal to 0. So therefore, by comparison principle, k tilde times b, let me call it k times b, dominates GL throughout. And therefore, in particularly over here. So therefore, on this set I get by some universal constant k times b is bigger than equal to GL. And what do I need to show now? That this u, I know what u is less than equal to u is bigger than equal to b, and I have shown that b is bigger than equal to 1 by k times GL. All I need to do is that I show that by some other k2 this GL dominates, right? And then I am in business, right? So this is what I will show now. I have already used the properties of the Green's function to know that on this part of the set, this part of the boundary, the Green's function is like a number, right? It's a number which is like bounded from above and below, because it's like mod x to the power 2 minus n, but mod x is like 1, okay? Well, half 1 by 10 million doesn't matter as long as it stays away from 0, okay? So you have to learn how to sort of identify the bushes and separate it from the end goal, which is the forest, okay? So now is the big, well, now I want to draw even a bigger, okay? So now what? So I have this bigger picture, okay? And here is my set. Now I take a smaller set. And then I take a test function, which is 1 in this part of the boundary and becomes 0 outside this, okay? So this is like half, this is like 3 by 4 or 5 by 6, 3 by 4, and this is 1, okay? So I have a 5, which is 1 here and becomes 0 by the time it reaches out over there, okay? And now I need to take a point y and I look at the following. I look at u times phi of y. Because phi is 1 over here in the set, this is equal to u of y, right? Agreed? And this is equal to, if I apply the Dirac property of the Green's function, this is just equal to minus L GL of y with u of y. So let's call it x and x dx. Agreed? This is the Dirac property of the Green's function. Qualitatively, everything is smooth, okay? I didn't even tell you how the Green's function is obtained. So if you just want to apply the L2 theory and the Banerjee-Nashmoser theorem, what you get is that the Green's function exists in a space which is like W1P, where P is less than n over n minus 2, okay? That comes from, it's not just the soft Lax-Milgram theory, but it is a hard application of the Banerjee-Nashmoser theorem, okay? You need both, so that you are in the Murray zone, and then you can use the duality. But then to prove a pointwise property like this, you have to get into this hard estimate. A classical approach to the existence of the Green's function is by the method of parametrics that you can find in this very beautiful text of Friedman, written in the late 1950s, okay? So there is a lot of theory that is going behind it, but qualitatively I'm assuming everything as smooth, so I don't even go to this L2 theory, okay? I assume that my Green's function exists by Friedman, the method of parametrics, which is not due to Friedman, by the way. This is due to Levy back in the 1930s, okay? So anyhow, so this is what it is. If I apply the divergence theorem to it, right? If I apply the divergence theorem to it, this becomes A grad GL, A grad GL, grad U phi. This is a bad term because this is going to live here. So I need to find a way of cancelling. But so far I have not used the equation. But let me write further. Plus A grad GL grad phi, good term because this is going to live in this part times U. And this is the strip. So let's call this strip C. So this is my enemy I need to kill. Okay? But I can kill it because so far I have not used the PD. So I also know that A grad U grad GL phi equals to 0. Right? So this product is 0, right? Because it is the equation satisfied by U. And therefore, if I expand it, this is like A grad U grad GL phi plus A grad U grad phi GL. And now I see if I subtract this or add this, then I can kill this, which is my enemy, which is living on this set. Okay, because this is the set I want to localize, because this is the set I will now apply my Carlson estimate. Okay, I have not really applied my Carlson estimate in a very sort of elaborate manner so far. Okay, so I will leave that at some point. Okay, so if I do this, then what I get is that modally Uy, which is U value here, is less than equal to 2 terms, which is less than equal to A grad G grad U, sorry, A grad G grad phi times U plus the sign at this point doesn't matter, A grad U grad phi times G. Now, if I look at this set, okay, here I apply the Cauchy square. So this is like grad G squared half over the set C, grad, so grad phi square is like 1 times U, and you have, okay, so you have U1, so it is like U squared and half, okay, plus the other way, which is grad U squared over C times G squared half. And this is all over the set C, right? Because grad phi is precisely supported in this strip. Okay, now let's look at this estimate. Grad G squared, because I'm far away from the pole, right, which is G of Y, I know that I can use the equation. So if I use the Cacciopoli estimate that Professor Adimurthy did, then I know that grad G squared over this set can be controlled by the maximum value of G, possibly over a bigger set. Right. Sorry, so let me draw other colors. So this is where I need pictures, okay? So this is the set. So I can compare it by the value of G in this set, which is still away from the boundary, right? In this yellow strip, it is still away. So grad G square is controlled by G square, but all the G values here by the Carlson estimate is controlled by the value of G over this set. All the G values by Carlson are controlled by the G at the top, because on this set I can apply the Carlson estimate, right, to G, because G is non-negative, and then I can compare it with the value here, and therefore I can compare it with G of Y x naught over here, because this is far away from the pole, right? I can apply the first from this, but all the values here are controlled by the values here, and this values by the Harnack is controlled by the values here, because I'm far away from the pole. Okay, so therefore, on this part, on G, I can control it by G of Y x naught up to a constant times now U square. Again, U is controlled by the value of U, but again by Carlson estimate, U is controlled by value of U where? At the top. And U of there is 1, right? So I can ignore U, because by Carlson, U is bounded, right? I can apply the Carlson on this strip. I'm not applying it on half the strip, but assume that the original problem is defined on Q 10 million, okay? So that this is like at least in half the strip. So you say as long as you're away from the boundary, I can do all my process. So all the values of U are controlled by U of 1. So U of 1 goes away. So this chunk is controlled by g of y x naught. And what about this chunk? Again, grad u square is controlled, grad u square in this region by Cacciopoli is controlled by a value of u in this region. But the supremum of u in this region is again controlled by 1, right? By Carleson estimate. So u goes away. So this part goes away because this is controlled by u square over a bigger strip. And again, the value of g over here is controlled by g of y at x naught. So integral of g square is again controlled by maximum of g, and maximum of g is controlled by g of y x naught. So all in all, what do you get? That u of y is controlled by a large constant c times 2 of g of l y and x naught, where x naught is this point. So you see that u is controlled by, from above, by a constant factors times g, and v is controlled from below by another constant factors times g. So therefore, u and v are comparable to one another, right? So this proves the boundary Harnack principle. Now I will show another argument due to Luis Caffarelli that shows that the ratio is bounded. And this proof is slightly more than the Moses, Harnack to Helder, because the ratio doesn't really satisfy an equation, okay? So you require a proof. So you see how how beautiful these ideas are? So now I will show, it is not just the final result, but the contour to the result, which is one of the striking aspects of this work of Caffarelli phase, Mozzola and Salsa. Okay? So now I will prove Helder. And the Helder is more like, I want to show that u by v is in C alpha near the boundary. So u by v is C alpha of omega intersection we have, where 0 is a boundary point. Okay? So what I do is the following. So I know that the ratio is first of all bounded. I normalize, so v by u. So let me just do v by u by v. Doesn't matter actually, u by v. Okay, so now what I do is the following. So in fact, you will see that one, if you knew already that u by v is bounded, then you don't require the sign of u. Okay, so I will write it as v by u because most of the time it is written like this. Okay? Doesn't matter what v by u is, but generally u is like the positive one and v would be anything. So you will see that if you knew that, if you had the knowledge that v by u is bounded, then you would not require the sign of v. That is my limited point. But that you would not know in this situation of Lipschitz domain that we have. But in a non-divergence form situation, this will be available to you. So that will lead to the well-known Krylov C1 alpha estimate that we will describe in a later talk. Okay. So first you require the knowledge to start the process that v by u is bounded. Okay. So what I do is the following. I normalize. Suppose I want to get that the ratio is bounded all the way up to the origin, which is at the boundary. So I want the picture. So at a far away interior point, what I do is that I take u of 1 to be 1. Well, don't assume 1 because 1 is like a one number, but take something, okay, vector, which is at a distance comparable to 1. Okay. So now what I do is that I look at, so I write A1 to be, AK to be minimum of by u over b 2 to the minus k plus and bk to be max of the ratio over the same set. Okay. Clear? So I do the first step, and so all I need to show is that bk minus ak is less than equal to some 1 minus theta times bk minus 1 minus ak minus 1. If I do that, then I can iterate, right? Because that is like the oscillation decay. So how do I do that? I have here 0. I have here like the value of u equals to 1. And here is how the graph lies, right? And this is between two constants. So this is the ratio u by v. This is trap between. So what I know is that, so if I have this to be v, so suppose this is the graph of v, okay, which goes to the boundary. And this is like, I know that b1 times u is trapping it from above, and from below, a1 times u is trapping it from below, right? So then what I do is that, then I look at the following quantity, which is, so I look at the omega w1, which is b1 of u. That's what I'm trying to say, that once you know that it is trapped, then you don't need the positivity of v. Because then you can take b1 u minus v over b1 minus a1, and W2 to be the other one, which is B minus A2 U A B minus A1 U over B1 minus A1. And you know that W1 of E plus W2 of E is equal to B1 minus A1 of U of E over B1 minus A1. Well, if at some point I know that B1 and A1 are the same, then I don't need to do anything, right? You can use the unique analyticity of harmonic functions or anything to know that it has to be the same Gauss-Stein ratio throughout, right? If I know that at some point they match, then there is nothing that I have to do, okay? So if they're not the same, which is where this argument is relevant, okay? Because I don't want to run into a zero. But if B1 and A1 is the same, then it's already good, right? Because then I know that they are the same function all throughout. Right? Up to a constant. Okay, so now you see that the sum of this is equal to U of E, but U of E has been normalized to 1. So therefore, one of them has to be bigger than equal to half. Either this is bigger than equal to half or this is bigger than equal to half. So let's pretend that this is bigger than equal to half. So suppose W1 of E is bigger than equal to half. And then from the general boundary Harnack theory, if I apply to W1 and U, I know that W1 has to be bigger than equal to C times U in P1 by 2. Okay? Because if I know that the ratio, and this is equal to 1 by 2 U of E, so therefore I know that the ratio is bounded in B half. This is the boundary Harnack theory. So if I know that two non-negative harmonic functions, okay, are normalized at an interior point, then the ratio is bounded in half the set. This is what is the quantitative restatement of that. Once I have that, then I'm done. Why? Because then I know how to sort of whether to truncate the oscillation from one side or the other side. This will just give me that. Let me write it more properly. B1 minus U is bigger than equal to B1 minus U over B1 minus B minus B1 U minus B over B1 minus A1 is bigger than equal to C times U. So if I write it out, what I get is in B half. So therefore, if I write it out, what I get is that B1U minus C times B1 minus A1U, C times B1 minus C times B1 minus. So this C will be like less than equal to 1. So let me write it as 1 by C, because otherwise this looks like I'm exaggerating too much. Okay? Because small c is typically like less than 1 bigger c. So I should write it as 1 by c. So then it's more reflective. Otherwise, you see, like you subtract something that is like negative, and that cannot be because b is like positive. Okay? This is bigger than equal to b in b half. What it is telling me that I have truncated the oscillation by a fixed chunk of b1 minus a1. You see? So from the top, if this situation happens, that W1 of E is bigger than this, that means that I have truncated the oscillation over here in my next level at some B2. So the B2 has to come down. And what is this B2? B2 is this quantity over here. That is a fixed chunk of the oscillation at the previous level has been truncated at this level, right? And so therefore it means that B2 minus A2 is less than some 1 minus theta, which depends on this 1 by C. It is exactly equals to 1 by C times B1 minus A1. So if I just write it out, I'm sure with even closing my eyes that B2 minus we have the advantage that Luis Caffarelli is not sitting in front of us. I can be more assertive. 1 minus 1 by C times A1 minus B1 minus A1. So the oscillation continues, right? If I repeat this, I get that the ratio is Elder continuous. So now with this, let me just tell you the one nice application, because later on when I do the small here, I will tell you that, and in fact that will be relevant even for the classification of the global solutions in the obstacle problem, the fragment Lindorff principle. Okay. So I will now give us, so this one I think I don't know who proved it for the first time. So there are various references you can check of Ancona and all others, which is uniqueness of non-negative harmonic functions in bones. So PHP2, so this is more classical, fragment Lindorff principle. So I have a cone. Okay, I have a cone. I have U and V harmonic, non-negative. Laplacian u equals to Laplacian v equals to 0. And I know that at u equals to v equals to 0 on the boundary of the cone. Then the fragment-Lindblom principle claims that u equals to some constant times v in the whole cone. And the positivity is very crucial over here. Okay? And so therefore, then you can recover it, right? It will be like R multiplied with the characteristic constant times the first eigenstate on where it sort of intersects, where it takes the arc with the sphere, right? So that would be the unique sort of, because you know that the ground state is all positive, right? So how do you prove it? Okay, so let's look at the proof. So these are more like revisiting the older theories by these powerful arguments, okay? And this whole idea of blowing up, that is zooming in, or blowing down, that is zooming out, these are very pertinent features in the proof of all these arguments. And this is something that you have to sort of internalize, okay? So of course, in these lectures, I understand it is very heavy, because when I first learned the proof from my advisor of this, how the boundary Harnack implies C alpha, he explained to me in 45 seconds. It took me 3 days to sort of reconstruct the whole proof. And he learned it from, I think, Dalberg or Luis Caffarelli. I'm not sure, in his Minnesota days. So I really love that principle a lot. So here it is, okay? So now I take this thing, okay? What I do is that I normalize the value at this interior point, u of e equals to v of e equals to 1. Now, if I have a far enough lambda, okay, very far enough, okay? So this is scale 1, and this is, say, scale some big k. So here, suppose I have u of k of e and v of k of e. The cone is over here, okay? I want to say that on the same line, this ratio is also bounded, because if this ratio is too large, suppose this ratio grows like some lambda, okay? Then, which is to say that if u by v at this point at k of e is like lambda, then if I take 1 by lambda times this, if I take lambda v and u, I will normalize this value at 1, and then I will sort of decrease this ratio. And boundary Harnack principle tells you that if this ratio over here is bounded, because then I can make it the scale 1, then this ratio cannot be too close to 0. What I'm trying to say is that if this is too large, and if I divide by this, I will have a very bad implication on the rescale functions at these points, okay? Then this will become too small, okay? And the boundary Harnack principle cannot allow this. So therefore, if I go along this line, I know that the ratio is bounded from above and below. It cannot be too small or too large, because then I can apply it to, instead of u by v, v by u, okay? So now, if I look at too far, and if I look at the function u tilde, which is u of k dot, and v tilde, which is v of k dot. Because of the property of the cone, the whole situation is scale invariant, right? So the one region, so what am I doing? I'm looking from far and I'm blowing down the picture. It is not like zooming in, it is like zooming out. I'm looking from far, right? So then what happens? In this new picture, I have that at 1, u tilde equals to v tilde is like almost 1, okay? And then this one region, the one region over here changes to 1 by k, right? And because of my uniform C alpha estimate of the ratio, what I will have is that u tilde by v tilde in this region, okay? And this value over here is 1, right? Minus 1 is as small as I want. Why? Because the ratio is held there. And this point is now what? This point, if this point is at a distance 1, then the one point in the rescaled picture is at a distance 1 by k. And because of the uniform nature of the C alpha estimates of the ratio, I can ensure that this can be made as close to 1. So if I now move this k to infinity, I can make this epsilon to 0. So therefore, it tells you that in this whole region of this new picture, or in the one region of the original picture, u by v has to be 1. And then, I mean, you can extend it by analyticity, or in the very first place, you can have done this in like square root of k region, right? Because square root of k region in this picture will be like 1 by square root of k. And if k is large, 1 by square root of k is also very small, right? Clear? Anyhow, I mean, you have to apply any of your favorite methods to extend. So therefore, if you have in a cone a scale invariant picture, blowing up or blowing down doesn't really matter. Okay. So this is another beautiful application of boundary Harnack. So the obstacle problem application will come later. Okay. So this would be the normal pitch of the talk, but the level is only going to go up as we go to more sophisticated topics. Okay. So this is like the minimal level of the lectures that you can expect from me. So it is not expected that you can take away everything, but I want to ensure that all the sweet spots are mentioned so that if you have to fill in the details, at least that becomes some reference point that you can sort of consolidate the details and try to work with this. So that's all.